Okay, I think we can get started. Hi everyone, I'm Shefali Garg. I'm a software engineer at Microsoft in Azure Software-Defined Virtual Networks team. I'm very happy to join you here from Seattle. Let me know where all are you joining me from. So in this talk, I have been working in this space for around 3 years out of 5 years in Microsoft. I'm working on improving the underlying Azure platform, as well as also building various customer-facing networking features and products. So in this talk today, I'm going to talk about software-defined networks, and we'll also take you on a journey down to the ongoing evolutionary phase of this cloud networking world. Let's get started. So in 2000s, the infrastructure of all the companies was used to build on traditional networks. By traditional networks, we mean like the networking functionality of that architecture was very much built on these devices like switches, routers, hardwares like ASIC chips. So the whole network was very much dependent on the hardware based on what protocols and software they support. How many of you have set up the internet at your home, like by yourselves? Let me know. When I first was installing the internet at my home, I just bought few devices like modems, routers, and cables, and switched them all, cable them all together, and yeah, I got the internet working. So imagine this. This was the same which was happening in data centers long time back. All the companies, they have all the devices by themselves, and if anyone has to change anything, they have to manually move and recable those devices. So as you can imagine, the networks were like very static and rigid, because unless there's a very critical thing, very critical, compelling reason, people generally don't change their networks very often. To scale this up in the present world, where we have a lot of data centers. So this is the one of the image for Microsoft Azure data center in Quincy. So around 2 years back, when I got a chance to visit this data center, I saw like they have around thousands of machines and servers installed in it. The cloud providers, they build all these big data centers all across the globe, and they rent out the individual machines or the portion of them to their customers. So imagine having this traditional model in these kind of data centers. Like it would mean like whenever we are renting out any machine, there will be some person manually moving and recabling or rewiring those devices. That would not have clearly scaled, right? So we needed a network which is dynamic so that we can route the traffics anywhere we want. We needed a network which is flexible so that we can configure it from our own place, like instead of going to those data centers. We needed a network which is cheaper so that it's possible to do all these networking innovations which are possible right now. So software-defined networking, it promised to solve this problem by taking the brain out from these hardware devices into a centralized controller. So earlier, all the devices, they know their own function, what they have to do. There was no central entity which can control the whole network or traffic. Apart from that, like in today's world, in SDN, this controller, it directs the destiny of each and every data packet going in and out from all the devices. When I say data packet, it means like contains a unit of information, like some bits of zeros and ones, the information which we want to send from one device to another device, right? So this controller, it sends those packet handling, those data handling rules to each of these switches, and these switches, they just forward the packet based on whatever the controller has set. So this centralized controller has end-to-end visibility. It knows about the whole network. It knows about all the traffic paths. So if from machine 1 to machine 2, there can be many multiple possible routes, right? So if one of the path is congested, so the controller knows about it and can redirect the traffic to some another path. So as you can see, networks are a bit smarter. It also gives a centralized point through software to configure all the devices. So instead of like having of manually configuring each and every device, now it's possible to change them all through one single point. On top of that, we can we can provision the network using the APIs, the application programming interface. So all the applications, they just program the controller using those APIs, and the controller then again program those devices using some APIs only. There was no manual intervention here. And instead of using those traditional and those proprietary and closed firmwares by each vendors, it was possible to use those open APIs and open protocols. So now we don't have to remember any such spatial proprietary syntaxes and commands from each of the vendors. So this, of course, will lower their operating costs because management is much easier. SDN, it also enables the separation of control plane and data plane. So it is possible to have both hardware and software to evolve independently. Instead of using those dedicated devices, we can just use the basic hardware, which only job is to forward the packets. And all the brain and functionality we put in the controller, the software. So networks were cheaper, right? So the SDN made the whole networks very much dynamic, very much flexible, and as well as cheaper. So to make the management of these networks much more better, virtualization was introduced. So network virtualization, it abstracts the networking connectivity and services into a logical virtual network, which we commonly know called VNets. How many of you have set up VMs in your computer ever? Like so VMs, virtual machines, they are kind of emulations of computer system. So you can create multiple VMs in your laptop or your computer. Although they are sharing the same hardware, they are sharing the same CPU, same memory, but they still behave like they are themselves a fully fledged machine by themselves, right? So similarly, the VNets, they were the logical abstraction of all the networking resources. They still share the same physical network, same cable, networking cable and router and all the devices. But it was possible to have the isolated networks, independent virtual networks, which are isolated from each other. Right. So this allowed the microsegmentation as well. It was possible to divide the whole physical network into multiple independent virtual networks. Also, like vice versa, we can also like combine multiple physical networks into one software-based virtual network. But generally, like companies, they create multiple VNets and assign them to the customers. And customers, they can configure the policies based on whatever they want. Like a company can have like HR department, IT department, and they they can have like their own different virtual networks, their own different networks. It reduced the network provisioning time because now it is possible to like provision the network based on few clicks. We just have to like select the devices which we want and the controller then just programs them. It's only possible because we are sharing the physical network. So the devices are already there, right? We just have to program few rules based on our policies. Failover, yeah. If any one device goes bad, yeah, we can just quickly fail over to another device. All the controller has to do was to program the rules to another device. Also helped in disaster recovery, since this is the logical abstraction, it's all the like virtual concept. It is possible to have multiple copies of those VNets in many different regions. So if one data center or one region's data center have some issues, it was possible to quickly fail over to another data center, or to have services or network in another region working. So network virtualization, the VNets, they further help the management of the networks. So when you create a VNet, a network, you will create multiple machines, those virtual machines, and then configure your own network. So these machines, they can land on any computers in the data center. Remember I told you like the data centers have like thousands of machines. So these VMs, they can land on any of them. We don't care, like the customers, they don't care where they are landing. However, the physical network, it works on the basis of physical addresses. Like all the networking machines, all the devices which are connected to a network have some a unique numeric label assigned to them so that the physical network knows like exactly where it has to dispatch those packets, right? So it needs like some identifier, some label which we give to these machines so that it knows like, okay, out of all these machines, this packet has to go there. It's kind of like our mailbox delivery system, right? So in virtual world, how does the package actually go? Because in the virtual world, all these VMs, they can have their own IP addresses. You can assign your own custom address to any of your VMs in the network. So how does it work? The VMs in a network, they create a normal packet. This is like like an example of the data packet. We have like the source IP address, destination IP address, and the payload, the actual information which we want to send to another machine. So the VM, it doesn't know about physical world, right? So it will just create a normal packet based on the customer addresses, the virtual addresses it knows. The platform, it then wraps this original packet with another headers which contain the actual source and destination physical addresses. Like the machines, the computers, they have their own physical addresses, the unique physical addresses. So the platform, it wraps the packet with those source and destination addresses. So now the physical address knows, like, okay, this is the source, this is the destination, this is the payload. So I just have to transfer this, dispatch this packet to this particular machine. Simple, right? And on the destination machine, the platform then again strips out this header. This outer header is again removed, and then we present the normal packet back to the VM. So the VM creates a normal packet, platform wraps it up with some information, dispatch it, and wraps that out, strips that out, and then present the normal packet to the machines. So this process of like having IP header inside another IP header is generally known as IP and IP encapsulation in the networking world. So as I told you, the VNets, they are isolated by themselves. Like all the machines in the network, they can talk to each other, but machines in different networks, they cannot talk. But it's possible, like we may want to connect these two different networks, like two different networks and two different regional offices. They may want to connect to them. So we can achieve them either by using gateways. So gateways are like some traditional devices. So we have a VNet, we put a gateway in front of it. Another VNet, we put another gateway, and there is a VPN tunnel, the secure tunnel. So all the packets from this VNet, they will go through these devices and then reach to the VNet. Right. The gateways, they can connect any two network, like two physical networks or two virtual networks. So these are like normal traditional devices. For virtual networks, however, we can use peering, VNet peering. So as you can see, there are no other devices in between the two VNets. Since the controller, it knows like where exactly the devices are, it knows about the whole network. So it can program uh, those devices and can do all these packet manipulations like engapping, degapping. It can do all the things with the packets and can deliver them to the other VMs in any other VNet. It can be in any other region without the use of any third-party devices. So since now there's one less network hop in the path, it gives a low latency connection. And also, we are not restricted by the bandwidth of any devices. So so this VNet peering helps us to get a low latency and high bandwidth connection. IP addresses, as I told, there are some numeric label which is assigned to every device which are connected to the network. So these IP addresses are managed globally by IANA, Internet Assigned Numbers Authority. So all the companies, all the providers, they buy the IP addresses from this authority for their use, for their own use. So IPv4 was the first version of addresses which we use. I think all should have like seen such numbers. So these are 32-bit numbers containing like 4 tuples of 8-bit each. So it means there can be at max 2 to the power 32, that is around 4 million unique IP addresses in the world. Gardner, on the other hand, predicted that there will be around 5.8 billion devices that will be connected to internet in 2020. So you can see the problem. We can only have 4 million addresses, and we have many more devices which wants to connect to the internet. And this is in addition to the large number of computers we already have in the data centers. So yeah, since there was like high demand and low supply, the prices was skyrocketing. It was getting expensive to buy the IP addresses. To solve the scale problem, IPv6 was introduced. So these are 128-bit addresses, which means we will have undecillions of unique IPv6 addresses. So it ensures the cloud providers that they can scale their data centers at much higher space as they want. It also ensures these these manufacturers of these IoT devices that their devices will continue to have unique identifiers for a very, very long time. On top of that, IPv6 was secure. It has IPsec, like the very good security algorithm inbuilt into it. It also provides efficient routing and more efficient packet processing. So this made the whole network like very much better, much secure, more efficient than ever before. All these improvements which are happening in this networking world. So as the networks were becoming better, uh, of course, like the government, healthcare, and financial institutions, they also wanted to onboard to the cloud, right? They also want to get all the benefits of cloud computing, like all the cost efficiencies and the ease of management. They wanted to use all these benefits. However, the one problem which was preventing them was compliance. They have like very strict compliance regulations. I mean, like data, like they care a lot, like what exact data is stored, where their data is stored, like data sovereignty, all these data transparency and data protection laws, all these different countries they have. So it was very important for cloud providers to be compliant with all those regulations. Security. These entities, they cannot afford to be compromised by anyone. So security was, of course, obviously, was very important for them. So the providers, they are solving this problem by one way is like having the separate clouds. So for example, in Azure, we have separate clouds in China, in Germany, for US government. So this ensures that not only virtual, but not only virtual, but as well as the physical network is also separated, like from the normal public cloud. So these countries or these separate different clouds, they only host their specific workloads, which is not used by different other public normal companies, normal customers. Apart from that, they also wanted to access the data resources securely. So for this, We introduce features like service endpoints and private links. So these features, they ensure secure connectivity of VNets to the data resources. Uh, as I told, a VNet is itself isolated. It is secure by default. Like all the machines, they can talk to each other, but no outside entity cannot, unless we configure some extra policies. But these entities, they wanted to access the data resources as well from the VNets directly in such a way that no other VNet can access them, and even the internet should not have access to their data. Right. So although all the packet, this whole network, it traverses only in the platform infrastructure. The databases, they don't know from exactly where this traffic is coming from. They only have the IP information. And these IPs, they can change because these are all custom IP addresses. Like I can have any IP address I want to assign to my VM. So how do we solve this problem? So what we did was we embed more metadata information like region ID, VNet ID, subnets, etc. in the packets so that it can uniquely define the source. We again did something with the packets, like we can modify, we can manipulate them, so that we can accomplish what we want. So we embed these packets with more information and send this different packet to the destination. So destination machine, it now knows like it's a different packet. So it parses the header, it identify the source machine, and then decide based on the controller policies, like, okay, whether I should allow or deny this source to access my resources. So the VMs in the VNet, they create a packet. The platform embeds more metadata information, more information, so that when they arrive on a destination machines, they can parse these packets, identify the source, like from where exactly it's coming from, and then based on the policies which controller has set on this machine, it can decide whether this VM should have access or not to my resources. So these features made the whole end-to-end traffic flow much more secure. So not only the VNets, but even the access to the different resources like databases or web applications, they were also secure. So as these networks were being used by those important institutions, it was more than necessary to have continuous monitoring. We can't afford to have multiple outages and we don't know, right? So it was more than essential to have automated systems which are monitoring both underlying physical network as well as overlay virtual network, and identify any connectivity or latency issues which are happening in the network. So we created an automated system so that all the machines in the VNet, they are tracking the connectivity of its system, of its network. So we introduced a virtual ping agent in the machines, which will periodically inject TCP ping packets in the network on the behalf of the host machine. So all the machines in the VNet, they can talk to each other. So the ping agent, it will periodically picks a machine in its network and decide okay, I want to send a ping packet to this machine now. Then after next few seconds, it will then send the packet to another machine, right? So it will keep on sending these ping packets. The controller is programmed with ping responder rules, so that on these destination machines, when these ping packets arrive, the machines can intercept them and inject the ping response packet in the network back to the agent. So this ping agent, it sends a ping packet. The destination machines will send a response packet back. So the ping agent then, based on this, like start time and the end time, it calculates the round trip time latency, like how much time it took to get back the packet, right? So we got the latency. It also notes like, okay, how many am I getting the response back or not? Like, so it calculates the success or failure of each ping packet is sending. So based on this, it's possible to have like both the connectivity and the latency issues happening in the network. So these ping agents, they record all this information and then send them to the monitoring systems so that we can have further alerting. So this helps us to have continuous monitoring and uh, allows us to have alerting so that we can get to know, we can mitigate them proactively before it's leading to a widespread outage. So networks already, they are like very dynamic, very agile, flexible, cheaper, secure, and being monitored continuously. However, they're still evolving to expand their capabilities to support many more use cases. Supercomputers. It's now possible to have your own supercomputer in your dedicated network. Earlier, when only those institutions they have access to high performance computing, now it's possible for customers to like have their own supercomputers, like dedicated supercomputers in their own virtual networks. 5G, SDN and virtualization has a very important role there. SDN allows this SDN controller, it allows the admins, IT admins to operate, to manage their 5G networks and introduce any more services or any changes in the network much faster. The controller, uh, the virtualization, it allows the physical network to divide into multiple virtual networks which are capable of supporting multiple radio access networks. So they both played a very important role in this 5G. Internet of Things. The massive amount of IoT devices we have, only SDN allows it to manage and automate the smart ecosystem containing the magnitude of the smart devices. So to wrap it up, I'll leave with a few takeaways. Software-defined networking, it enabled the separation of control and data plane. It made the networks cheaper, agile, and flexible. Virtualization, both virtual machines and virtual networks, they were the core component of cloud computing. They made the networks much more manageable. Like they gives a logical abstraction so that we can have the same physical resources, but we can still have virtual copies and we can all share them together. IPv4 addresses, they are near extinction. World is running out of v4 addresses. So IPv6 addresses helped us here, and all the companies, all the providers are gradually moving to support v6 addresses. Security of whole network, whole end-to-end traffic flow is critical. These, especially for these government and financial institutions where we have like very strict compliance requirements. Security is very important for them. I mean, it's important for all of us, of course. The large platforms, they need continuous monitoring and proactive mitigations. It is essential to monitor both the physical as well as virtual network and identify any issues which are happening in the network proactively so that we can mitigate them earlier, yeah, before the customers they have like widespread disruption in their services. So these were the few takeaways on SDN and virtualization VNets which you can have. So here are the few of the references, like few of the patents which my team has. So you can take a look further. Thank you so much for your time and kind attention, and stay connected. You can follow me on LinkedIn or Twitter here. I'll open up now for questions. Any questions you may have, type in the chat window and I can answer them. Okay. What do this mean? Yeah, I shared my LinkedIn in the slides. I'll share it again here as well. So controllers, they have like we are creating more partitions of these controllers. This controller is a software. We have like one software, but it's like a multiple copies. Like we have partitioned it, we have replicated it. It's like a distributed system. It's a software which has like multiple copies, so that if one software system is down, we can another system, another copy of it can still work. So yeah, in the distributed system world, like we don't have like single point of failures. We generally have like multiple copies, partitioned, replicated, so that you can receive a graded number seems like yeah, same, yeah. So to avoid the single point of failure, yeah. So in the software we are using those distributed systems. There's some kind of high availability setup for the backup. Yeah. Okay, contact information. Yeah, let me share them. LinkedIn has this and Twitter. I just started out with cloud computing with no ITOCS background. Okay, for cloud computing, like for software-defined networking, especially, you don't need any networking knowledge at all. Like you don't need to know how these devices work. However, like since it is all the software world, we still use all the software principles like basic languages like C++, C Sharp, or using those distributed systems like Kafka or like Service Fabric. So I would advise you to have like basic fundamentals of CS, like data structures and algorithms, and like basic software engineering, like the knowledge of distributed systems. Yeah, you don't need any like any networking knowledge is not required. It's like a normal software world. So so we, as I told, like we have multiple copies. So and in even in the physical world, like we have like different paths, different routes. So if one goes down and one network, like one device has some issue, or software in one region has some issue, like maybe like as we're deploying new bits, it's possible, right? Like some like one particular slice or one particular partition has a problem. So it's possible to roll back the software, and it's also possible to reprogram to a different devices. Yeah, only basic software engineering knowledge. You don't need any networking knowledge because it's all software defined world, right? As I told, it's we don't care about about hardwares in SDN world, in the virtual world. Yeah, you own for the controller to program these controllers, to build these controllers, we are using the basic software engineering skills. We are using the open source APIs. Yeah, yes. The open flow open source APIs. We in Azure, like if you, I can only talk about Azure. So in Azure, like we provide lots of machines, lots of virtual machines, framework. Like you can create your networks, you can create your virtual networks and VMs like based on whatever. Like we provide different alternatives, so you can use any of them which fits your demand needs. Like some of them are very cheaper, some of them are very expensive. So based on the requirements. Like if you just need the normal processing, normal programming, you can use the basic devices. By backbone, I meant like the platform infrastructure. So the all the packets, they are not flowing to the internet. Like the right now the internet which we have on our phones, on our computers, they are all the packets are going through the normal internet, like normal world, through the IP providers, ISP providers. But when I said backbone, it means all the packets are only flowing through the infrastructure, like in the Azure platform, only traversing the machines which we have in the data centers. It's not leaving the basic platform. It's not going outside that. Yeah, thanks Virginia for sharing the book. So SDN architecture, it means like we have like one single system. We have like one controller, control plane. And VNets are like the abstractions which we have. Like we create multiple VNets inside that. So the same controller is programming different VNets, like the different devices for different VNets. So it's like we have central controller, but we have multiple VNets. They are being supported by the same controller, like same software. Any other questions? So when I said controller, controller means the software. So we have like a single, it's like a software is a distributed system, which contains various microservices but distributed system, but it has multiple copies which we deploy in different regions so that they can program differently. Like one region does not cause an outage in another region, but they still can program multiple devices in the same region, and they can support multiple VNets, multiple virtual networks in the same physical network. So it's like a single controller, but we are programming multiple virtual networks, multiple devices. We are specific. It allows us to provision different policies for different tenants, like different customers we have. No, it is not that complicated, but yeah, the single controller is able to handle multiple routes. Yeah, and the traffic is like tremendous, like, and it is increasing day by day. Yeah, it's a single software, but that software itself is very complex and it's able to handle that many traffics and that many decisions. Yeah. Okay, I think we are out of time now. I think the recording will be, they will share the recording and I'll see where I can share the slides as well. Yeah. Thank you so much, everyone, again. I will not hold you back to attend more sessions. Yeah. Thank you again and have a wonderful rest of your day. Thank you. Bye.